Today we are going to have our last full lecture. We're going to finish up coverage of chapter 11 and get into chapter 12, which is radiation. And as I said during lecture the last time, we're going to modify the content coverage for the last exam such that it will not include chapter 12, which is the chapter on radiation that we'll go over today as an introduction. So the last exam, which is on Wednesday, will only cover as modified from chapter 8 through chapter 11, which is chapters 8, 10, and 11 through exchangers. So I'm going to start sharing my screen so I can get back to the problem that we were working on the last time. And just to recap, we were covering the effectiveness NTU method. So there was a problem. Well, let's see, I'm to express the effectiveness NTU method. It's just another method by which we can analyze a heat exchanger that is different from the log mean temperature difference method. And actually, so I can contrast those two, we solved the problem with the log mean temperature difference method, but here, that log mean temperature difference method was initially developed for the analysis of a double pipe heat exchanger, where that double pipe heat exchanger could be in the configuration here where both fluids flow in the same direction, which is a parallel flow heat exchanger, or for the analysis of a double pipe heat exchanger where it's a counter flow where they flow in opposite directions. For any heat exchanger fluid, whether it be the cold fluid or the hot fluid, we can always assess the heat transfer rate into or out of that fluid by the capacity rate, which is the mass flow rate times the specific heat, times the temperature difference that fluid experiences. So for the cold fluid, it's going to gain heat. The hot fluid is going to lose the same amount of heat. So those two expressions always apply for any heat exchanger fluid, such that we're only assessing the change in enthalpy of the fluid as it moves through the heat exchanger. When we consider that all the heat lost by the hot, gained by the cold, is transferred between the two fluids, then we get into this expression of, well, how do we write that expression? For the log mean temperature difference method, it just says that heat transfer rate for the energy or the heat that is lost by the hot and gained by the cold transferred between the two is this overall heat transfer coefficient times the surface area times the log mean temperature difference, where the log mean temperature difference is just an expression of the average temperature difference that exists along the length of the heat exchanger when at least one of the fluids is changing with a nonlinear logarithmic expression, such that here we can see that the temperature for the hot fluid is decreasing from a given point to some value that will be the constant temperature once there's no more heat transfer between the two fluids, so that it is the temperature difference at position number 2 minus the temperature difference at position number 1 divided by the natural log of the ratio of those two temperature differences that occur between the hot and cold fluids along the length of the heat exchanger. This expression doesn't change, so that all it's doing is giving us an average value of delta T1 and delta T2 along the length. That expression is defined slightly differently with regard to the inlet and outlet temperatures. When we have a counterflow heat exchanger, delta T1 and delta T2 are still just the temperature differences between the hot and cold fluids at the inlet and exit. But delta T1 for the parallel flow heat exchanger is the hot inlet minus the cold inlet, and delta T2 is the hot outlet minus the cold outlet. In a counterflow heat exchanger, here, delta T1, since I have the hot fluid coming in on the left and the cold coming in from the right, delta T1 is the hot inlet minus the cold outlet. And delta T2 is the hot inlet minus the cold inlet. So the definition of the log mean temperature difference stays exactly the same, but whether we're using hot inlet, hot outlet, or cold inlet is going to depend on the flow arrangement. Joseph, yes, it has delta T1 but please just review your, that was probably covered in your calculus class. If you just rearrange the expressions, the sign will change on the expression of the natural log of the ratio of those two terms. So will the sign change on what is in the numerator when you change the positions around. The log mean temperature difference will be exactly the same. So they're exactly the same expression. So when we're writing these expressions for the log mean temperature difference to calculate the heat transfer rate between the two fluids, it's very direct in that Q dot is UA times the log mean temperature difference when we use a double pipe heat exchanger. But for the other arrangements, the shell and tube and the cross flow heat exchangers, in order to use the log mean temperature difference method, we have to consider a correction factor, because in those two flow arrangements, the heat exchanger of hot and cold fluid inlet and outlet temperatures are not in the same positions. So in order to use these three expressions, the amount of heat transferred out of the hot, the amount of heat transferred into the cold fluid, those stay exactly the same, but this expression for the heat transferred between the two just requires a correction factor, and that correction factor is going to be a function of the properties associated with the particular fluids and the heat exchanger arrangement. So when we're considering those two types of heat exchangers where we want to use the log mean temperature difference method, it requires that we use these figures that were referenced the last time here in order to find the correction factor, that is F. Then we have to consider not only the flow arrangement, but the calculation of this capital R and capital P that are defined according to temperature differences between the hot and cold fluids that are flowing into and out of the heat exchanger. So we take that correction factor that is on the y-axis here, and we'll assess that value for the conditions that exist for that particular heat exchanger in order to then calculate that heat transfer rate that exists between the two fluids. And this is through this expression is where we're able to find, let's say, what the overall heat transfer coefficient would be, or what the surface area, the shared surface area for heat exchange has to be in a given heat exchanger if we have, some temperatures that are given and and the temperatures that are required for a given heat exchanger. So when we're using that log mean temperature difference method, that method is defined according to the expression of how we relate the actual heat transfer that's occurring between the hot and cold fluids with regard to the geometry of the actual heat exchanger. Now, when we're considering the effectiveness NTU method, we're still writing expressions for the heat transfer out of the hot fluid and into the cold fluid according to the capacity rates. But now we're defining the expression of the heat that's transferred between the two fluids as Q dot is this effectiveness times Q dot max, where Q dot max is defined as the minimum capacity rate, which is just the lower of the two fluid capacity rates, times the largest temperature difference that exists in the heat exchanger, which is the hot inlet minus the cold inlet. So this will define Q dot max for this method, and we'll also consider that the effectiveness of the heat exchanger is a function of the number of transfer units and this expression that's called the capacity rate ratio. And here we use another set or use a set of tables. And actually in your text, there are figures that represent that are representations of these equations that are presented in the table that we also reviewed the last time. Table 11.4, which has the effectiveness as a function of the number of transfer units and the capacity rate ratio. And then there's in table 11.5, the same information, but the number of transfer units is defined in terms of the effectiveness and the capacity rate ratio. Here we use the expressions that correspond to the type of heat exchanger in order to write an expression that allows us to get to a description of the geometry of the heat exchanger, which comes through the expression of the number of transfer units. When we look at this expression of the number of transfer units is the overall heat transfer coefficient times the surface area divided by the minimum capacity rate. Well, this is the expression through which we're able to define things like the overall heat transfer coefficient given all the other quantities in a particular heat exchanger. So if I pull the heat exchanger off the shelf and I supplied a hot fluid and supplied a cold fluid, if I measure the mass flow rates of those two fluids and the inlet and outlet temperatures, then I get the capacity rates, I get the temperature differences that would occur. And if I've selected that heat exchanger with a note where the surface area that is shared for heat exchange is known, then I can actually calculate what the overall heat transfer coefficient is. And I could do that through the expression of the effectiveness in terms of the relationships that were presented in table 11.4 or 11.5 and write those expressions such that I could calculate the heat transfer into and out of the hot and cold fluids here and just solve for the expression of the overall heat transfer coefficient. And that's how we get these expressions in a previous figure here where there were ranges of overall heat transfer coefficients for different types of fluid combinations in lots of different heat exchanger types, where we have these ranges of values of overall heat transfer coefficients that are functions of not only the heat exchanger geometry and fluid combination, but also there will be variations in the velocities of the fluids, which will give us different values of heat transfer coefficients. But those two methods for heat exchanger analysis are both valid for the determination of particular quantities, and depending on the depending on what you seek to determine, you might select one method over the other method, in that these analyses, for some problems, the log mean temperature difference may be a little bit more direct to get the quantities that are asked for. Typically, the log mean temperature difference method is more suitable for determining the size of a heat exchanger based on the outlet and inlet temperatures being known. If the desired temperature, if you're given a particular heat exchanger with a known value for an overall heat transfer coefficient, often the effectiveness NTU method is a little bit easier to use to find, well, what the outlet temperatures would be if they're unknown. But for either one, you can do both. It's just that the number of calculations that you might have to make there might just be a few more steps necessary to actually solve that particular problem. But both of them, the effectiveness NTU and the log mean temperature difference methods, can both be used to solve for any of the quantities that might be unknowns in a given heat exchanger. So we were looking at this shell and tube heat exchanger, and actually at the very end, I made a mistake. I actually multiplied here when I got the capacity rate of the cold fluid. I actually multiplied two times 2,670, which was the specific heat to get 5,340, but it's actually larger. It should be 2.1 times that number. So I'll need to, before we finish this problem, I need to go back and recalculate that quantity so that the analysis will be correct here. So let me get my calculator back up, and this should be 2.1 times 2,670. So this, so rather than erase it so that in your notes you can see it too, this should be here 5,607 for the minimum capacity rate, or for the cold fluid, which was the minimum capacity rate of the two, because the capacity rate of the hot fluid was 7,209. So Cmin and Cmax stay the same. Now here the effectiveness will become a little smaller because this value should be 5,607. So here we have 252,315 divided by here 5,607 times 70. All right, so this would be 0.643 here for the effectiveness, and the capacity rate ratio changes slightly because this again is 5,607 divided by here 7,209. All right, so this should be 0.778. All right, so now I have correct values. And so in this problem, we were asked to determine, well, what is, let's see, which one was it? Yeah, for an overall heat transfer coefficient of 800 watts per meter squared Kelvin, what will be the required surface area? Now here again, that surface area that we are calculating is the surface area for heat transfer to occur, in that we have, this is a shell and tube heat exchanger where the water is coming in through and moving through the shell. The ethylene glycol is moving through the tubes. So the ethylene glycol is on the inside of one of these tubes and the water is on the outside. Here, the water, or the ethylene glycol is the fluid that experiences a temperature increase. So that's the cold fluid. And the water is experiencing a temperature decrease. So it is the hot fluid. So the heat transfer is from the water into the alcohol. Now, the place where the water is giving up its heat is on the outside of the tube, so that the surface area on the outside of the tube would be used to determine what that heat flux is into the tube. And the surface area on the inside of the tube where the alcohol is flowing is another surface area. But again, in a shell and tube heat exchanger, or any heat exchanger where the fluid is moving through a tube without any fins on it, the surface area on the outside and the surface area on the inside are essentially the same, because we take these tubes are made of a very thin-walled material, so that the difference in the diameter or the radius from the inside to the outside is negligible, so that if the surface areas are the same, then whether we're looking at heat transfer from the hot fluid or into the cold fluid, that surface area that is shared is considered to be the same value. So when we're looking for a calculation of the surface area in the shell and tube heat exchanger, we're considering that the surface area on the outside of the tube that this ethylene glycol is running through is the same on the inside and on the outside. So if we're looking for the surface area, it comes from the definition of the number of transfer units, such that the surface area would be the number of transfer units times the minimum capacity rate divided by the overall heat transfer coefficient. In this problem, the overall heat transfer coefficient is given. The minimum capacity rate was determined once we calculated the mass flow rate times the specific heat for the cold capacity rate. And we calculated the capacity rate of the hot fluid based on the amount of heat that was leaving the hot fluid divided by the hot inlet temperature minus the hot outlet temperature, because we weren't given a mass flow rate for the hot fluid. So we determine the capacity rate of the hot fluid, and we compare the two. The larger of the two is C max, and the lower of the two is C min. So we have the overall heat transfer coefficient, the minimum capacity rate, and now we just need the number of transfer units. Well, just like the effectiveness is a function of the number of transfer units and the capacity rate ratio, where here, this is the capacity rate ratio here. The effectiveness for this heat exchanger is just the actual heat transfer rate, which would be that heat gained by the cold fluid, lost by the hot fluid, divided by the minimum capacity rate times the T hot in minus T cold in. Well, we can actually calculate the effectiveness. So if the effectiveness we can write as a function of the number of transfer units and the capacity rate ratio, well, the number of transfer units can be written as a function of the effectiveness and the capacity rate ratio. Again, we have the capacity rate ratio that we calculated, and we can also calculate the effectiveness for this heat exchanger by this definition of the effectiveness as being the heat transfer rate divided by Q dot max, and Q dot max is the minimum capacity rate times the maximum temperature difference in the heat exchanger. This effectiveness then is the heat transfer rate of 252,315 watts. And I'll just put the units in for this one just to show that they do certainly cancel. The minimum capacity rate is that of the cold fluid here, which is 5,607 watts per Kelvin, times the temperature difference. Oh, I already calculated that. I thought I calculated this. It's here. The effectiveness is 0.643. So, and just to put the units back here, this is watts in the numerator, and the denominator on this 5,607, that's watts per Kelvin times the temperature difference, which would be, this temperature difference is the same in degrees C as it is in Kelvin. So what we're left with is watts divided by watts, which is a unitless quantity that describes the effectiveness. So this number of transfer units as a function of the effectiveness and the specific or the capacity rate ratio allows me to then look for the expression of the number of transfer units in terms of the effectiveness and the capacity rate ratio for the type of heat exchanger we have. We have a heat exchanger that is a 2-shell pass, 8-tube pass heat exchanger. So when we go back to the tables for the effectiveness NTU method, here again, we have in table 11.4, the effectiveness as a function of number of transfer units and capacity rate ratio. In 11.5, we have the number of transfer units as a function of the effectiveness and the capacity rate ratio. So here for shell and tube heat exchangers, here it's a 2-shell pass. N number of shell passes. So here we can say 4 N shell passes. So we'd use this expression to determine the number of transfer units, where our effectiveness here was 0.643, and the capacity rate ratio of 0.778. So 0.643 and 0.778. Substituted here again. Now this effectiveness one that you see here is based on the effectiveness that would be the expression for the heat exchanger with just one shell tube pass. Now, here we have 2 shell passes, so we just directly use the expression of the effectiveness in this expression. You would only have to find the effectiveness as F minus C, where F is equal to this expression if there was only one pass for the heat exchanger. But since we have 2, we just directly use our expression of the effectiveness here. Substituting these values for the effectiveness and the capacity rate ratio into this expression yields a calculated quantity for the number of transfer units. So here, this is from table 1115. You're calculating. You're calculating NTU from table 11 dash, I think that was 5, and we'll confirm here. Yeah, table 11, I think dot 5. Then we get that the number of transfer units based on the effectiveness of 0.643 and the capacity rate ratio of 0.778, this number of transfer units is 1.7. Now, once this number of transfer units is, now the number of transfer units is a unitless expression, just like the effectiveness and the capacity rate ratio are both unitless. But now we can calculate the surface area. Now is 1.7 times the minimum capacity rate ratio, which is 5,607 watts per Kelvin, divided by the overall heat transfer coefficient, that was 800 watts per meter squared Kelvin. So here you can see that the expression of the surface area will just have square meters, so that this expression that we determined for the surface area, 1.7 times 5,607 divided by 800. This is 11.915 square meters. So that surface area could be calculated if the surface area on the inside or the outside for the pipe that carries the ethylene glycol. Again, here, so if the inside diameter, or here the outside diameter, is here DI and DO are approximately the same for a thin-walled tube, then the surface area on the inside would just be pi DI times the length of the pipe. The surface area on the outside of the pipe would just be pi DO times the length of the pipe. But this surface area that we calculated could be set equal to either one of these. So here, 11.915, 11.915 square meters. So that if I select the diameter, here where again the inner and the outer diameters are considered to be the same for a thin-walled tube, then once I select the diameter for a known surface area that will be required, this will tell me how long that pipe would have to be. Now, of course, the expression of the diameter and the length are going to effectively change what the value of the overall heat transfer coefficient would be. In this problem, it was given, but we know from chapter 8, if we change the expression of the diameter through which the pipe is flowing, we change the Reynolds number, so that the Reynolds number for an internal flow will be the velocity times the diameter divided by the kinematic viscosity. So as I increase the diameter of the pipe, of course, the velocity would decrease for the same mass flow rate, and I would get a lower value of the Reynolds number. And by getting a lower values of the Reynolds number, of course, that means now that I have a different expression for the variation of the heat transfer coefficient through that flow, through that pipe. And that's going to affect what the average heat transfer coefficient would be along the length of the pipe, and thus it would affect the expression of the overall average heat transfer coefficient through the heat exchanger. So when making changes to a heat exchanger, because of all of the consequential effects of changing the velocity or changing the fluid or changing the diameter or length of the pipe, these expressions of these overall heat transfer coefficients have to be empirically determined, meaning that we have to actually take the heat exchanger as it's fabricated or as it's designed, connect in a hot or two fluids so that one is a hot and one is a cold fluid, measure these temperatures. So here we have these expressions of the heat transfer rate into the cold fluid and out of the hot fluid. We can always make these calculations. We measure the flow rate. If we know the fluid and use the specific heat of that fluid at the average between the inlet and outlet temperatures, where we're actually measuring those temperatures, we can determine exactly how much heat is lost by the hot fluid, exactly how much heat is gained by the cold fluid, and thus be able to consider, well, how much heat is transferred between the two fluids here, where that would be in the numerator of the definition of the effectiveness of that heat exchanger. But this expression is how we would eventually find out, well, what is the overall heat transfer coefficient? We can do exactly the same using the log mean temperature difference method, because in the log mean temperature difference method, we can calculate, again, the energy lost by the hot fluid, gained by the cold fluid, exchanged between the two fluids, so that we can write expressions of this correction factor in terms of the type of heat exchanger that it is, and calculate a log mean temperature difference based on it being in a counterflow arrangement, where we're assuming an arrangement that looks like this for the calculation of a log mean temperature difference for these shell and tube and crossflow heat exchangers, to then find that overall average heat transfer coefficient along the length of that heat exchanger. So when we get into heat exchanger analysis, because of the complexity of two fluids moving at different velocities with different configurations for the flow paths, this expression of that overall heat transfer coefficient will vary according to any variations that you make into the heat exchanger, whether that be the fluid type, the fluid velocities, and of course the geometry of that particular heat exchanger. But these two methods can be applied to any of the heat exchangers that that include those double pipe, shell and tube, and the crossflow heat exchangers. It's a matter of being able to measure the measurable quantities to then calculate the ones that are not directly measurable. So even in the case of the surface area that we just calculated, that's based on an expression where we considered that for this problem, the overall heat transfer coefficient, oh no, this was, here we go back down a little bit here. The overall heat transfer coefficient was given, but in typical cases, if you design a heat exchanger, you know what the surface area is, and you can measure all these other things, the temperatures, the flow rate, etc., and then calculate what that overall heat transfer coefficient is. Much time is often spent let's say for this shell and tube heat exchanger, you set the geometry, and then you run through multiple variations, typically in the mass flow rate of the fluid. So let's say if I deliver the ethylene glycol at a given temperature and I deliver the water at a particular temperature, those are things I have direct control over, along with that mass flow rate. And then I just measure the outlet temperature of the ethylene glycol and measure also the temperature of the water, such that if I increase the mass flow rate of the ethylene glycol, let's say here, we were given the mass flow rate. If I increase the velocity of the fluid, then the temperature decrease, or I mean the temperature increase of this cold fluid will be smaller, in that because there's less time available for the ethylene glycol to move through the heat exchanger, because of the increased mass flow rate, we'll see a smaller temperature change to occur in the fluid, and thus that's going to affect the heat transfer rate that would occur into that fluid, and it will propagate other changes in the heat transfer coefficients that would exist along the flow path, and thus we would have different values of the overall heat transfer coefficient. So when you see a heat exchanger, whether it be online or you're looking through a catalog, and there's a range of values for the overall heat transfer coefficient, the company that designed that heat exchanger either directly did the calculations, or they sent it out to a third party that specializes in doing just that, just measuring overall heat transfer coefficients for different heat exchangers, where they're measuring things that are directly measurable, mass flow rates and temperature changes, and using either a log mean temperature difference method or an effectiveness NTU method to then be able to calculate what that overall heat transfer coefficient would be, which embodies here the expressions of two convection resistances on the inside and on the outside of the surface that is separating the two fluids, and that conduction resistance at minimum 1, because we can have others that will be added here if I have oxidation on the inside of the pipe or oxidation on the outside of the pipe. That adds 2 more conduction resistances that allow me to take into account what is the resistance through the base material that the tube is made of, and what is the resistance through any oxidation that might occur on the inside and or the outside of the tube, so that it will increase the resistance between the flow of heat out of the hot fluid and into the cold fluid, and thus change the expression of the overall heat transfer coefficient, so that if I have additional conduction resistances due to oxidation, it will reduce the overall heat transfer coefficient that exists to represent what would be 5 resistances at that point if I added 2 more resistances due to conduction because of the oxidation. Now, in chapter 11, again, we're pulling together concepts from chapter, I think that was 3, for the construction of resistance networks, where particularly we're taking into account the conduction resistance through the solid and the convection resistances. We're also considering concepts from chapter 8, where which allow us to calculate heat transfer coefficients based on flow conditions, and consideration that heat transfer coefficients do change along the length of a flow path. So those are put together in the expressions of heat exchange between hot and cold fluids. Now, for the last of the concepts that are the modes of heat transfer and body of concepts, we'll consider radiation. Now, radiation is definitely the most complex of the 3 modes of heat transfer, and is particularly complex because of all of the factors that affect the quantities that we consider when we're making radiation calculations. When we talk about radiation, this is a mode of heat transfer that is energy or thermal energy that is transmitted or transferred by electromagnetic wave propagation. So here, there's no participating medium. Consider conduction. The heat transfer was by the diffusion of energy through a solid piece of material or a fluid that's not moving. We consider convection, it's between a solid surface and a moving fluid. But when we get to radiation, there's no there's no required participating medium, so we can have heat transfer between two surfaces, let's say surface 1 and surface number 2, and there doesn't have to be any medium in between the two in order for heat to transfer back and forth by radiation. Now, this allows us to classify radiation as what we call a surface phenomenon. And this surface phenomena, with it being a surface phenomena, the conditions of the surface are going to greatly affect what the expressions of the heat transfer rates will be. And when we're considering radiation, we have a multitude of factors to consider. We have to consider the material type. Is it a metal? Is it wood? Is it a plastic? We have to consider the surface condition. Is it polished? Is it rough? Are there layers of some other substance over the top? We also have to consider the temperature of the surface. And through the material type and the surface condition, those give rise to expressions of the emissivity of the surface. We also have to consider two other quantities associated with radiation, which are the absorption, or let's say the absorptivity, and the transmissivity, where the absorptivity is an expression of how much energy is absorbed. The expression of the emissivity is how much is leaving the surface just due to its temperature. Transmissivity is, well, how much of that energy passes through the material. And we definitely can't forget reflectivity. The reflectivity of a surface, particularly in the visible light range, is what allows us to see surfaces, see images, see anything. Basically, if all surfaces absorb visible light, then there will be no light left to reflect. And thus, the only things that we will be able to see are those things that actually emit light. So we turn a light bulb on so that that bulb emits visible light that is then reflected off of surfaces that don't emit light so that we can then see them. So if we're in a room that has no windows, and if the only source of light is a light bulb, if the light bulb is off, we can't see anything. When we turn the light bulb on, that light emanating from the light bulb then reflects off of surfaces and into your eye, which allows you to perceive it as an image. Now, I'm going to refer to some figures because it's really hard to talk about radiation without the use of figures because we can't see those electromagnetic waves that are actually propagating the energy, particularly the thermal energy. And that thermal energy is very limited in its range of wavelengths that we would consider the radiation to actually occur. So here in this figure, we have some plants, furniture, people, and walls. All surfaces above 0 Kelvin emit thermal radiation. So whenever we're considering measurement of heat fluxes or heat transfer rates by radiation, we have to always take this into account, is that radiation or thermal radiation is always occurring for surfaces or objects that have a temperature greater than 0 Kelvin, such that the higher the temperature, the higher the heat transfer rate by radiation. And that radiation that is being emitted, let's say by this guy here that's sitting in the chair, well, if he's emitting radiation and everything else in this room is emitting radiation, the furniture, the plants, and the walls are emitting radiation, well, we're all interested in, well, how much energy is being emitted from the person that's sitting here, but also how much energy is that person absorbing from the surfaces that are around them. This is the reason why, if you've ever, your skin is extremely well suited for measuring heat fluxes. It's not as good for assessing temperatures, but definitely for heat fluxes. And just to, as an example of why it's not, that your skin is not very good for measuring temperatures or assessing temperatures. If you've ever gotten into your car that has been sitting in the sun and everything inside is hot. Now, if the air temperature, let's say it's 95 or 100 degrees in your car, if it's been sitting in the parking lot in the afternoon, or maybe even a higher temperature than that, you know that if you sit in the car and you touch the leather steering wheel, or let's say, or it's maybe some type of vinyl, if you touch that, it may be too hot to touch. But if you touch the seat, which would be at exactly the same temperature, if it's a cloth seat, the temperature of that cloth seat and the temperature of the steering wheel would be the same temperature. They typically be the same temperature as the air that is inside the room or inside the cabin of the vehicle. But when you touch the steering wheel, it may be too hot to touch, but it may be quite comfortable to just put your hand on the same seat. The reason that you don't perceive, or that you perceive the steering wheel to be hotter, is that the heat flux from that vinyl when you touch it is much higher into your skin than the heat flux from the cloth seat to your hand. They'll be at if you put a thermocouple on them or put a thermometer right next to them, you will find that they are exactly the same temperature, but the heat fluxes are very different because of the thermal conductivities of the two materials, in that heat has to transfer from that material into the skin on your hand, so that when you touch vinyl compared to when you touch the fabric, the thermal conductivities are very different. And so the temperature gradients are different into your hand, which are, when multiplied by the thermal conductivity of your skin, are going to give you a heat flux. So your skin can measure heat fluxes or assess differences in heat fluxes much better than it can temperatures. This is also the reason why when you walk past a cold window in the wintertime, if you're walking down a hallway that has windows and the windows are not covered by drapes, you may feel the hairs on your arms stand up. That's because the heat flux by radiation, if there's a window here that is exposed to cold air, of course, the glass on the window would be much closer to the cold temperature outdoors than the interior drywall. So if you're walking through the room or down the hallway and you get to a window that doesn't have drapes on it, that cold glass is much colder or much lower temperature than the drywall that you were previously walking past. And if your arms are uncovered, the heat flux by radiation from your skin to that cold window is much greater than the heat flux from your skin to a warmer drywall. And when that heat flux from your skin increases, thus the heat out of your skin increases, your the blood flow to those areas will change, and the nerve and the muscles in your in the skin, or not the muscles, but the nerves in the skin will cause those hairs to actually stand up due to the constriction of blood vessels to reduce the amount of heat that you're actually losing through your skin there. So when we're considering heat fluxes, our skin can calculate or can detect them very well. I mean, if you have your eyes closed while you're walking outdoors on a sunny day, you can tell by the heat flux into your skin when you're walking in the shade compared to when the sun is shining directly on it. That direct heat flux from the sun is detected by your skin, and when that heat flux is taken away just by shading it, you can usually perceive that without even looking. But again, the skin can detect those heat fluxes very easily, and thus for radiation, where changes in heat flux can be significant, we can assess those heat flux changes not only through your skin, but also through particular devices that we call pyrometers and bolometers that measure heat fluxes. But these heat fluxes that we measure are actually in a very small range of we call the electromagnetic wave spectrum. And this spectrum here is based on wavelengths, lambda. Lambda is a wavelength, and it's typically reported in microns, which are just micrometers. Micrometers here. So this is 1 times 10 to the minus 6 meters. By the frequency in radians per second, where the speed of light, we'll say this is the speed of the propagation of an electromagnetic wave through a given medium. So the speed of light, where light is, we're talking about visible light, it's the speed of light in a vacuum. So if you see what is right expression here, this is the speed of propagation here through of a wave through a medium. So the speed of light actually through water compared to through glass, through air, is different because of the way that the wave, that electromagnetic wave, interacts with the molecules of the substance through which it's actually propagating. C sub 0 is the speed of light in a vacuum. And this is the speed that is used, speed of light in a vacuum, and it has units of meters per second. So that these expressions of these ranges of the wavelength are a function of the or consideration of the speed of light as a quantity taken as 2.9979 times 10 to the 8 meters per second. Now, how do we get the speed of propagation of wave through a medium? Well, this is a relationship between C and C sub 0, where the speed of propagation of a wave, now here the wave is any of these wavelengths here, is equal to the speed of light through a vacuum divided by n, where n is the index of refraction in that medium. So we actually can change the speed of light by allowing it to propagate through different types of material. So when the speed of light is changing through a prism, that's when we can get the separation of colors out of taking from visible light into different colors that make up visible light. But now here, just kind of zooming in on this range of wavelengths here that describe at the top electrical power waves, but here more specifically radio and TV waves. These wavelengths are from 10 to the 5 to 10 to the 10 microns. So that wavelength are very long for those types of waves. Then we have microwaves. This is the same microwave range in which, or range of wavelengths in which your microwave oven is working. Then we have just below microwaves is the top of the thermal radiation range. Now the thermal radiation range is that range of wavelengths through which we would consider thermal energy to be transported. So that's so basically molecules, atoms, electrons of a given substance, when they absorb or emit that energy, it changes their temperature. So this thermal radiation that I referred to before is continuously emitted by all surfaces, all materials that are above a temperature of 0 Kelvin. So all of this energy that is thermal radiation will be emitted as infrared or distributed through the infrared range and the visible light range and a portion of the ultraviolet range. Ultraviolet is from 10 to the -2 to 10 to the minus, well, this should be, 10 to the minus, well, actually, look and see exactly what the ultraviolet was, because I forget exactly where it ends, because the thermal radiation range is 0.1 to 100 microns for what we call thermal radiation. So the thermal radiation range is made up of the range from infrared. Infrared is that part of the radiation range that we use infrared cameras for. So that light or that energy that is emitted from surfaces that is not in the visible light range, that our eyes can't detect it, but that will, let's see if I remember this correct. This would be 0.4 to 0.7 microns is the visible. Actually, I think I have that here on the next one. Yeah, 0.4, and actually go all the way to 0.76 to not round it. 0.4 to 0.76 is the visible light range. From 0.76 to 100 microns is the visible light range, infrared, which ends at or begins at the end of the visible light range if we're going from top to bottom. And then from 0.1 to 0.4 is part of the ultraviolet range. Now, the ultraviolet and the infrared, we can't perceive with our eyes. 0.4 to 0.76, we can, such that entire range is the visible light spectrum. So often I'll make references to visible light when talking about thermal radiation, and that's only because since we can see things, it's easy to make analogies for the entire thermal radiation range. Now, this part of the ultraviolet range that is from 0.1 to 0.4 microns, where the entire part of the entire ultraviolet range goes from 0.01 to 0.4 microns. This expression of this just very upper part of the UV is where we get this. This is the part of the thermal radiation range that is typically damaging to colors, and that will bleach, let's say, plastic products that have dyes in them. If they're exposed to the sun, the dyes will be bleached, or in many plastics that are exposed to ultraviolet, they tend to harden or become brittle due to their exposure. Generally, ultraviolet light is not very good for your eyes or your skin, but this ultraviolet range is what that many sunglasses are going to block when you're considering wearing them out to protect your eyes. But that is a portion of the thermal radiation range, which again we take from 0 to 100 microns. Again, this infrared range that is from 0.76 to 100 microns. You may hear of near infrared or far infrared thermal cameras or thermometers, and they're just referring to if it's near infrared, is typically anywhere from 0.76 to about 10 microns, meaning that it's near the visible light range. Far infrared just says it's on the upper portion, up above typically 50 microns, up to 100 microns as a detector's range of operation. So our eyes can perceive all of the visible light range, but it doesn't perceive ultraviolet and infrared. And of course, since we're human beings, and that's where our limitation for our detection of thermal radiation that we call visible light, that's the reason, we designate what these are. These are not, the names of these ranges or the specifications of these ranges are decided on by those who did research into the electromagnetic spectrum, and then would group or specify particular ranges. So we have cosmic, gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, etc. Where again, the thermal radiation range is just that range that includes all of infrared, all of visible, and part of the ultraviolet range. Now, when we're considering the visible light range, it's further subdivided into what we perceive as colors. So again, if the ultraviolet range is part of the thermal radiation range, and again, it's just below the visible light range. At the bottom of the visible light range, right next to ultraviolet, is where we have our first color that sometimes we call purple or violet. And then as we increase in wavelength, we go from violet to blue, green, yellow, orange, and eventually to red, where these are colors that make up all of the visible light spectrum, such that in the presence of all of these colors, we have what's called white light. So that when you shine white light through a prism, you can get it to refract colors, and we can see rainbows, or water droplets act as prisms that allow us to see the rainbow when those water droplets are suspended in the air, such that they form a large prism that bends the light so that we can see all of these different colors. Now, when we consider radiation, these colors, or which are defined according to these wavelength bands or wavelength ranges here, only if that surface can emit enough energy in these bands to see these colors will we actually see them. So when you see a red laser, that red laser is a result of providing electrical power to a substance such that it allows for it to emit electromagnetic waves in the wavelength range that our eyes perceive to be red, and it is primarily only producing that wavelength somewhere in this range. I think typically for most lasers, somewhere between like 0.64 and 0.68 microns. Now, often they will list it as, let's say, 640 nanometers, which is just considering the same length unit instead of being written in microns, if we move the decimal point 3 points to the right, then that makes this, instead of 0.76, 760 nanometers. But you can get other laser colors, but it just requires that you be able to provide energy to a substance that is going to emit energy in that particular wavelength, so that our eye sees that color, that particular color. Now, something of interest in that, all of this gives us white light when they are together. In the absence of one of these colors, then we change the tint so that instead of it being white light, it will be some other color. If we intensify one of the colors, we can get the light to be perceived much more like that particular light. So when you see the headlights with a blue tint to them, or street lights that have a yellow tint instead of white, well, those are indications that the method by which the light is being produced is one such that there is a distribution of the intensity of the emission of one or more of these lights, or a decreasing in the intensity of another, that will give you something like a bluish tint or an orange tint or a yellow tint rather than a white light. And it's just differences in the distributions of these colors, which are just different wavelengths in the white light, or what we call visible light range, that is from 0.4 to 0.76 microns for all of the what we call visible portion of the electromagnetic wave spectrum. And we'll talk a little bit more about these distributions through a representation of what we call Planck's distribution, which tells us about the intensity of emission for radiation. Now, in order to talk about that, we have to define what we call a black body. And a black body is an idealized surface that emits and absorbs thermal energy. So this is an idealized surface for analysis of radiation emission and absorption. And it is used to actually compare to what we call real surfaces. So when we talk about a black body surface, a black body surface is one that for which no other surface can emit more energy. And actually, I'll write that as a list in a second, but to pay particular attention to what's depicted here, notice here, if I'm measuring angles from 0 degrees to 90 degrees here, this says that these red lines are an indication of the intensity of the emission from this surface. The arrows are moving away from the surface and outward. So these are indications of what we call emission. When a black body surface emits radiation, it does so uniformly in all directions. This would be called a diffuse emission. So that means if I take a heat flux measuring device, particularly a radiation heat flux measuring device, like a bolometer or pyrometer, and I mount it here, if I mounted it at 45 degrees, or if I mounted it at 5 degrees or 90 degrees to the surface, I would get exactly the same measurement of the heat flux, no matter what angle I'm at, from 0 to 90 degrees. For a non-uniform distribution of the emission, this would be called a non-diffuse surface, well, a surface that emits so that it has non-diffuse emission. If I consider the same angles, 90 degrees, 45 degrees, and let's say 5 degrees here, I would get different measurements of the intensity of the emission due to as depicted by these arrows here. So when I'm considering these kinds of these surfaces, if I wanted to, let's say, calculate, or if I wanted to know what the heat flux is by radiation, the heat flux by radiation, by emission, is going to be a function of position, or here a function of angle from normal, or here from parallel, from measuring 0 degrees to 90 degrees. But if I'm moving through different angles and I get different values of the heat flux, then that says that there is a directional dependence for the radiation heat flux, in that if the surface has a non-diffuse emission associated with it, then I'm going to get different values of the heat flux as it's measured as a function of some angle variation from this particular surface. So when we're calculating heat fluxes or measuring heat fluxes, we have to consider that there's a directional component that is going to affect what the value is for that measured heat flux. Now, before I get to the spectral black body emissive power distribution, I want to go back to this black body surface. Now, the black body surface emits the maximum amount of radiation from its surface at a given temperature. So what that just says is, here, I'm just going to stay with this figure here. If I consider that there's a temperature associated with this surface that is emitting as a black body, if that surface temperature, I don't know, let's say the surface temperature is 500 degrees C. If the surface of this real body is the same temperature at 500 degrees C, the black body surface will emit more radiation than real surface does. And that goes for any temperature. The black body will emit more radiation than any other surface at a given temperature. Now, that makes it an idealized body. The real body, the black body surface, can be compared to a real body, and it becomes the standard that is used for the determination of the radiative properties of a real surface here. Now, the black body, not only does it emit the maximum amount of radiation at a given temperature, but it's also what we would consider to be a perfect emitter and perfect absorber. Now here, with regard to a perfect emitter, it's referring to it being a diffuse emitter, in that the amount of energy emitted normal to the surface will be exactly the same as it emits parallel to the surface at any angle in between. If the heat flux is 100 watts per square meter here, it's also 100 here, 100 here, 100 here, and even parallel to the surface. Whereas we can see here on a real surface, the intensity of the heat flux changes as we move through different angles here. So the black body surface is that idealized surface, but it's considered to be a perfect emitter and perfect absorber, and we get maximum emission from a black body surface at a given temperature. Now, along with that emission, it being a perfect emitter, is also a perfect absorber. Now, a perfect absorber just says, imagine, well, if it's absorbing, that means energy is coming in from the surroundings, so in the opposite directions. That perfect absorber just says, no matter what the direction is from which energy is coming to the black body surface, it will absorb it. And it absorbs all of it. So the consequence to it being a perfect absorber is that no light can actually reflect off of a black body surface. Reflection is that amount of energy that comes to the surface and is reflected off of it. Well, a black body surface, being a perfect absorber, doesn't allow for any reflection to occur. Now, it sounds kind of, I mean, it's an idealized surface. The real surfaces are not perfect absorbers, but for particular wavelength ranges, some surfaces can approach becoming perfect. And you see this if you ever go to the movies, or if you've ever been in someone's home who has a home theater, or if you ever took the time to really notice when in a classroom, when the screen is pulled down, the white screen is pulled down, there's a black edge around it. And if you get close, you'll see that the white surface maybe has a little bit of, depending on what kind you have. There's some white surfaces that will be slightly shiny or have like a polished look, or some, depending on what kind it is, it may have a slightly matte finish. But on that black edge that surrounds the white area, that's almost always a matte finish. And the reason that is there is that it does not reflect visible light very well. Well, you can consider that if I have a screen and I have a black edge here, let's see if I can make that thicker here. Let's see, so let's say I have a black edge around that white screen. Now, when you use a projector when you use a projector, you project in this white space here. But the image coming out of the projector is not always a perfect square. And it may not be a perfect square because of some imperfections in the lens. Also could not be a perfect square because there's a slight angle in that if the camera, or if the projector's lens is not exactly in the center and the length out to each of these diagonals is the same, you may have something of a trapezoidal effect, so that if it's angled upward, across the top is longer than across the bottom, and you do the best you can to adjust it. But when that light bleeds off of the white area onto the black area, if that surface does not reflect the light that came in from the projector, it's not going to be reflected into your eye. And so you would perceive this to be a clean square or rectangular shape, depending on what the white space is shaped like. But you won't see the light that bleeds over onto the black matte finish, because it behaves very much like a black body surface in the visible light range, with all of that light that's coming out of the projector and onto this screen. If it's not reflected off the black matte finish, then all you see is what's reflected off of the white surface. So it looks like a nice clean picture. Whereas if you remove, maybe you scroll the screen up and you let this just project onto a large white wall, the edges don't look as clean. And that's because all the light that hits that white wall or light colored wall is going to be reflected, and there's no control over the edges at all. But that's a case where that surface behaves like a black body surface for the visible light spectrum. But when we talk about a black body surface, not only does it absorb all visible light, but it also absorbs all of the infrared, and it absorbs all of the upper part of the UV to make up all of the thermal radiation range. So regardless of the wavelength, regardless of the direction, from which that energy is coming in, a black body surface will absorb all of that energy. Now, the expression for the black body emissive power, that energy that is leaving the surface, here with these red arrows, the emission for a black body surface, E sub B, is just equal to the Stefan Boltzmann constant times the temperature raised to the fourth power. This is what we call black body emissive power. So in order to calculate the black body emissive power for a given black body surface, all we need is the temperature, so that we can multiply it by the Stefan Boltzmann constant. Now, the Stefan Boltzmann constant, this lowercase sigma, here, this expression is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth power. So if I multiply that by the temperature raised to the fourth power, now this temperature has to be in Kelvin. This temperature is raised to the fourth power and multiplied by the Stefan Boltzmann constant. It leaves us an expression of the black body emissive power that is it's a flux. It's a watts. It has units of watts per meter squared. So here, if we want to calculate, well, how much energy is leaving a black body at a given temperature, then this is exactly how we would calculate it. Now, this expression, black body emissive power, comes from the consideration of an expression that we call the black body, or the spectral black body emissive power. It's a plot. Now, this comes from a significant amount of research done in physics to determine exactly what this distribution looks like. And we'll come back to this again. This is E sub B is sigma times T raised to the fourth. That's the black body emissive power. Now, here on this plot, this is a spectral black body emissive power, E sub B lambda. Now, E sub B lambda is here the spectral black body emissive power. And it has units of watts per meter squared micron. So where the micron here is in the denominator. And this is because the spectral black body emissive power, with it being spectral says that it's a function of wavelength. So on the y-axis, we have the spectral emissive, or what we call the spectral black body emissive power, as a function of wavelength here. Now, if the black body emissive power has units of watts per meter squared, and we look at this plot, this is the spectral black body emissive power, watts per meter squared per micron, as a function of wavelength, which is in microns. The black body emissive power is actually just the integral of one of these lines for a particular temperature. Notice here that each one of these lines has a temperature associated with it, from 100 Kelvin all the way up to 5,800 Kelvin. Each one of these lines is for a constant temperature condition, so that the area under this curve that's 100 Kelvin compared to the area under the curve for 5,800 Kelvin is related through the temperature, in that the area under each of these curves, for each of these curves that has a temperature associated with it, is the Stefan Boltzmann constant times that temperature raised to the fourth power. So when we're considering what these expressions are indicating, the black body emissive power is actually the integral, and we write this integral from 0 to infinity of the spectral black body emissive power, d lambda. This would be the area under this curve. Now, the integral is taken from 0 to infinity as the bounds so that we capture all of the area that might be under this curve. Now, for the black body emissive power, let's say for 5800 Kelvin, this line starts here and is up and over. And I say I'll just project it all the way back down to the x-axis. Well, beyond wherever it intersects the x-axis, actually I'll draw it in green here, the value is 0. Everywhere to the left, on the left bound of that 5800 Kelvin, that's also a 0. So if I integrate from 0 to this point, or here, let's say from 0.1 to this point. Well, the contribution to the area under the curve would be 0. Everything beyond where this line, if I projected it all the way back down to here, it's a 0. And so there would be no contribution. Now, because the black body emissive power is to describe all of the energy that is in the thermal radiation range, right? The thermal radiation range. The thermal radiation range is actually only from 0.1 to 100 microns. So here, 0.1, from 0.1 to 100 microns. That is the thermal radiation range. These green lines that are indicated past 100 microns, we're calling, well, what's after 100 microns? This is all thermal radiation. After 100 microns is the microwave energy range. So what this just, and so I'll just go back here. So we have thermal radiation from 0.1 to 100 microns. Above 100 microns is our microwave. Below 0.1 is the rest of the ultraviolet. So look here. Here, this gets right into, above here is microwaves. And below here gets us down into the ultraviolet. When we're considering calculation of the black body emissive power, E sub B, well, that's the black body emissive power in the thermal radiation range. So we're actually only concerned with the area under the curve between 0.1 and 100 microns. We're writing the expression of the integral from 0 to infinity just so it covers all of the entire range. But when we're calculating this quantity for the thermal radiation, well, we'd actually be limiting this expression. So the black body emissive power, if we wanted to expand this, we could write this as from the integral from 0 to 0.1 of E sub B lambda d lambda plus the integral from 0.1 to 100 microns E sub B lambda d lambda plus the integral from 100 microns to infinity of E sub B lambda d lambda. So we could break up this integral such that here, this second portion is only the thermal radiation range. Here, this is all of those. If we start at 0, this would include X-rays, gamma rays, cosmic rays. But E sub B lambda from 0 to 0.1 would be exactly a 0. So this would be the integral of 0 d lambda, which would just be a 0. Out past 100 microns, if we're considering the spectral black body emissive power for the calculation of thermal radiation, we would consider from 100 to infinity to also be a 0. So we're actually only considering what is in the thermal radiation range, that is 0.1 to 100 microns. This expression of this green line is just to show that for a black body, it emits radiation in all of the thermal radiation range, but it can also emit in the microwave, it can account for microwave emission, but microwave emission is not a part of the thermal radiation emission. Now, the other thing to note about this family of curves is notice what's happening with the area under the curve. The higher the temperature, we go to 100 to 300. The higher the temperature, the greater the area under the curve, meaning that the higher the temperature, the higher the value of the black body emissive power, which is just a flux, watts per square meter. So as we increase from 100 Kelvin to 300 Kelvin to 500, we get more and more area under the curve. Also notice what's happening to the value of the peak emission. So here at 100 Kelvin, the peak emission is, let's see if this is 0.01, and this is 1. So I'll say this is like 0.4 here. The peak emission is just 0.4 watts per meter squared micron. But as we increase the temperature, the peak value continues to increase. Also, so we have that the air, as we increase the temperature, the area under the curve, which is the black body emissive power, is increasing. Also, the peak value of the spectral black body emissive power is increasing. But the other thing to notice is that the peak is shifting to the left as we increase the temperature. So here for 100 Kelvin, just clean this up a little bit here. At 100 Kelvin, the peak value is, this is probably around 30 or 40 microns. So that peak value occurs here. At 300 Kelvin, the peak is about here, shifting to the left. At 5800 Kelvin, the peak is about here. So as the temperature increases, the area under the curve increases, the peak value for the spectral black body emissive power increases, and that peak occurs at a shifted wavelength that is shifting to lower wavelengths the higher the temperature is. Now, here, notice, again, this is from 0.1 to 100 microns is the thermal radiation range. So again, 0.1 to 100 microns is thermal radiation, all of the thermal radiation range. Visible light, 0.4 to 0.76 microns is visible. 0.76 to 100 is the infrared. Now, again, this is spectral emissive or spectral black body emissive power. At 100 Kelvin, now recall 100 Kelvin is certainly much lower than room temperature. 100 Kelvin minus 273.15 will give us the temperature in degrees C. So this is a negative with regard to value of degrees C. Here we'll talk, so I'll skip the 100 Kelvin just so that we can consider something more familiar. 300 Kelvin is about room temperature. So a black body surface at room temperature is going to emit radiation. Again, any surface above 0 Kelvin is going to emit radiation. What is the emission from a black body at 0 Kelvin? It's the Stefan Boltzmann constant of 5.67 times 10 to the minus 8 times 0 Kelvin is just 0 emission. If it's at 0 Kelvin, it emits nothing. But at 1 Kelvin, 2 Kelvin, 3 Kelvin, the black body emissive power is going to increase with the temperature. So here at 300 Kelvin, if I multiply here at 300 Kelvin, the black body emissive power would just be 5.67 times 10 to the minus 8 watts per meter squared Kelvin times 300 Kelvin raised to the 4th. So that's how we would calculate, well, what is that black body emissive power? And so that quantity that is the black body emissive power here, 5.67 times 10 to the minus 8 times 300 to the fourth power. This is a heat flux of 459.27 watts per meter squared. So that will be the flux when that black body surface is at 300 Kelvin. Now, look at the range, where that range of the spectral black body emissive power lies on the x-axis. It's here from 1,000 microns all the way down to just over 1. So I'd say this is probably about, with this being a log plot, this is probably like 2 to 3 as the wavelength here. So from here to over here. Notice I put these designations here. 0.1 to 100 microns is the thermal range. So from this green line all the way to 100, that's all of this area under this curve here would be representative of this black body emissive power. Now, the lowest wavelength which any of this energy would be emitted at 300 Kelvin, if it's about 2, then that's all infrared, no visible light. So that means if I have a black body surface, let's just imagine that surface as just a cylinder. So here we'll say that this is the surface temperature. If this cylinder has a surface that behaves as a black body, when I raise it to a temperature that is 300 Kelvin room temperature, so the TS, the surface temperature here, is 300 Kelvin, it's going to emit radiation in the thermal radiation range of 0.1 to 100 microns, only in the range from 2 to 100 microns. So that means it's all infrared. So what that says is, if I turned off the light, I would not be able to see this rod because it's not emitting any energy in the visible light range. And so I would have to use an infrared camera to actually see this cylinder that's behaving as a black body and emitting its energy at 300 Kelvin. It's not emitting any energy in the visible light range, so I would not be able to see it unless I turn on a light that provides visible light from a bulb that is then reflected off of this surface and back into my eye. Then I could see it. But with the lights off, because no visible light is emitted from this surface, I would not be able to see it. Now, what happens when I increase the temperature of this cylinder? That I'm saying the surface behaves as a black body. What happens if I raise the temperature to 1,000 Kelvin? All right, so I go from 300 Kelvin up to 1,000 Kelvin. Well, at 1,000 Kelvin, the black body emissive power is 5.67 times 10 to the minus 8 times 1,000 raised to the fourth power. And here, this black body emissive power is now 56,700 watts per meter squared. So I go from 300 Kelvin with a black body emissive power of 459.27 watts per meter squared to when it's at 1,000 Kelvin, the black body emissive power is now 56,700. So when I'm looking here at the area under the curve for 1,000, Kelvin as the temperature, that's the line that I'm on. So I have much more area under the curve compared to when I had the same surface at 300 Kelvin. Now notice here, the distribution still for the visible light, or for the thermal radiation range, is from 0.1 to 100 microns. But now notice that the peak is shifted over to the left. And now this distribution ends here. This is 0.1, this is 1. So this is down like at 0.4 microns. This band, this double black, these two black lines here are for the violet and red. So the violet begins at 0.4, the red ends at 0.76. So these two lines here, this line 0.4 and this line 0.76. So what this says then is that I have a distribution. Part of the distribution of the spectral black body emissive power at 1,000 Kelvin falls in the visible light range. Some of it is in the visible, and the rest of it is in the infrared range for the, as far as the thermal radiation range goes, from 0.1 to 100 microns. So what does that mean? That means that energy is being emitted with in the infrared range. So I could still use a thermal camera to see it, but I could also visibly see it because there's energy being emitted from this black body surface at 1,000 Kelvin that falls in the visible light spectrum. But now notice here, at 0.4 microns, that's violet. At 0.76 microns, that's red, where we go from red to orange to yellow, blue, green to violet. So, well, I guess green, blue, violet. But notice here, here's the intensity of that emission that's red. Here's the intensity, I'm sorry, erase the orange line here. The intensity of the energy that is violet. And then we have this distribution, again, violet to blue to green to yellow to orange to red. Now imagine, well, what color would this cylinder look like at 1,000 Kelvin? Well, the red would have the highest emission, violet would have the lowest emission, with the distribution being that it's increasing as we go to red. So this is going to probably be mostly a red color because the intensity of the emission in the range that is the red range of the visible light is going to make it appear to be red, even though I have a distribution, but the distribution is such that it's decreasing towards the violet. So it's certainly not going to be white light, because in order for it to be white light, the distribution across the range has to be almost uniform from violet all the way to the red. So this is, if this surface is at 1,000 Kelvin, well, 1,000 minus 273 is 727 degrees. Well, that would be if that's a black body surface, it's going to appear to be red hot, in that it's going to emit radiation that is red, with the distribution decreasing as we move toward the violet. Now, if I increase the temperature even more from 1,000 Kelvin to 2,000 Kelvin, if I go to 2,000 Kelvin, of course, the peak shifts upward and it shifts to the left here. Now, notice here, when it crosses through the band that is the visible light, here I have red and here I have violet. So the difference in the intensities between red, red, orange, yellow, green, blue, violet, because the difference in the intensities is less compared to the difference in intensities when it was at 1,000 Kelvin, here, this may be more like an orange or a yellow color associated with it, but it would be closer to being white light than it would at 1,000 Kelvin. And when we look at the emission here, 2,000 Kelvin, the black body emissive power is just a Stefan Boltzmann constant, now multiplied by 2,000 raised to the fourth power. Here, the black body emissive power is 907,200 watts per meter squared. So it goes from 56,700 to 907,200 watts per square meter. So much higher heat flux. And much more of this energy is being emitted in the visible light spectrum. And we get all the way up here to 5800 Kelvin. Now, 5800 Kelvin is the standard value for the temperature that we take as being the temperature of the sun. So here, when we look at the distribution, of course, we have more area under the curve. The peak value of the spectral black body emissive power is shifted to the left and it's higher. And now look at this distribution. Here we have the violet, here we have red. We have an almost uniform distribution of the intensity of the emission across these colors, and we get much closer to a white light, or what we call natural light or sunlight, that is a much more like a white light. And we can produce artificial lights where we can get these intensities to be almost exactly the same by using other means. But as far as the sun behaving like a black body surface at 5800 Kelvin, we can see that this distribution becomes almost uniform in the visible light spectrum, so that we can see, that's what we perceive to be white light or nearly white light. But here, when we consider, well, what is the heat flux here at 5800 Kelvin, the temperature that we take as the temperature of the sun, if it's behaving as a black body surface, this black body emissive power is 64,164,500 watts per meter squared. So that's what we consider the black body emissive power when it's behaving as a black body at 5800 Kelvin. Now, these express now, and here again, we get more like a white light. This is the reason why if you ever put, let's say, a piece of metal, usually like put a piece of iron into a fire, and you watch it. If it's initially at room temperature, it just it looks the same until the temperature increases enough that it begins to emit first red. With the red will have the highest intensity. If you look at the curves of all of these curves, if I drew families of curves between 500 Kelvin and 1000 Kelvin, we would see that as the temperature increases, we get an intersection first with the right-hand side, which would be at 0.76 microns for this black line here, meaning that the first colors that would begin to be emitted from that surface as it's heating up would be reds, and then it will produce red with some orange, red with some orange and yellow, red with some orange, yellow, and green, red with orange, yellow, and orange, yellow, green, blue, and eventually the violet. But until we get at these much higher temperatures where this peak shifts into this range of the visible light, it will be dominated by the appearance of the red colors, because as we increase the temperature, the red is going to be the highest value or have the highest intensity in that particular wavelength range, which is up around the 0.76 microns. So when we look at, well, how do we get, the white light that comes out of fluorescent bulbs? Certainly the fluorescent bulbs are not the temperature of the sun. Well, the temperature of the sun, or the sun behaving as a black body, just says that I have to emit all of these ranges at a very high temperature. In a fluorescent bulb, we actually are taking particular gas molecules and exciting them with electricity such that they emit what we call photons that are emitting or vibrating on this at the same frequency, or in the same frequency range of all of the violet and red. And depending on the intensity or the mixture of gases and the intensity of the energy that's being used to excite them, you can get a distribution of light so that you can get nearly what we might consider it to be white light or fluorescent light, but often it has a slight blue or slight, depending on the light, slight blue to green to purplish color associated with it. And that's because the excitation of those molecules is not based on heating up those molecules to a temperature which they will behave like a black body, but they are actually, it's much more like what we do with laser pointers, in that we excite particular molecules of a substance to get it to vibrate at these particular, well, at frequencies that correspond to wavelengths that fall in the visible light spectrum. Now, this red line, this red dashed line that's drawn through the maximum on each one of these lines, or each one of these temperatures, the green lines here, that is a result of what we call Wien's displacement law. Wien's displacement law just says, I'll just draw it here. Wien's displacement law is used to describe the position on the x-axis where that wavelength, where that maximum wavelength should occur. It just says that lambda times T max, which just says where the max wavelength, or where the maximum black body spectral emissive power will land, lambda times T is equal to 2,897.8. And this is micrometer Kelvin, as this is just a wavelength times a temperature. So let's say, going back to the 300 Kelvin, the room temperature. If I want to find out, well, what is the wavelength at which this maximum emission would occur? Now, if I project down here, that's almost right at 10 microns from this chart, but I can calculate exactly where that would occur. If lambda times the temperature of 300 Kelvin is equal to 2,897.8 micrometer Kelvin, then this says that lambda is equal to 2,897.8 micrometer Kelvin divided by the temperature that is 300 Kelvin. So this will be just under 10 microns. So 2,897.8 divided by 300. So this is 9.66 microns. So that's where the maximum wave, it doesn't tell us what the value is of the spectral emissive powers. It doesn't tell us what this peak is on the y-axis. It just tells us the location of the peak on the x-axis. If we look at, well, where is it for the solar, or for the temperature of the sun? Lambda times 5,800 Kelvin is equal to 2,897.8 micrometer Kelvin. So lambda is equal to 2,897.8 divided by 5,800. So here, let's see, divided by 5,800. The maximum wavelength is 0.499 microns. So that falls in the range of the visible light spectrum, which is 0.4 to 0.76 microns. 0.499 is just around the center of the visible light spectrum for a black body emitting that emits for a temperature of 5,800 Kelvin. Again, the temperature that we consider to be the temperature of the sun. So by these expressions of these green lines, depending if it's a black body surface, depending on its temperature, the distribution of all the energy that is emitted by that black body will change, such that at low temperatures, where the maximum wavelength is up in the infrared range, we don't have, any energy being emitted in the upper part of the UV or the visible light spectrum. It's all in the infrared. So if you consider, let's say if your skin was approximated as a black body surface, well, your skin temperature is close to room temperature. So that says, my skin does not get hot enough to emit in the visible light spectrum. All it can do is emit in the infrared spectrum. So this is the reason why when you turn off the lights in a room, and if you're standing in the room with another person, you can't see that person in the absence of some external light source. If you take an infrared camera and you shine it at that person, you can, because the infrared camera can detect the infrared energy that is being emitted from that person through the lens or through actually it's a bolometer that's in the device, and it can detect this energy that is emitted. The way that we have to turn on the light so that the light that is emitted from the bulb can reflect off that person into our eyes. So basically what we're doing is we're providing an external source for visible light to reflect off of that person and back into our eyes, and then we can see them. But we never get hot enough to actually emit visible light so that someone can see us in a dark room. The only way that they can see us is if that light is emitted from a different source and reflected off of a source that is not emitting visible light. Now, considering that incident light, or that light from an external source, there are different things the reason that we perceive colors. If we have white light that is made up of the red, yellow, green, blue, and sometimes we don't include the violet here, but violet will be one of those colors that you can perceive on let's say in a rainbow when the white light refracts. But if I have essentially white light hitting the surface and I see red, all that means is that the red is primarily reflected and the other colors are absorbed. So when you look at someone's shirt and it appears to be blue, it means that the white light that hit the surface is absorbed with the blue primarily being reflected. Now, that doesn't mean that it doesn't reflect any of the other colors. It just means that the intensity of the light in the range that we consider to be blue. So if I go back up to here, when I look at the colors, blue is 0.44 to 0.49 microns. That just means that the intensity emitted in this wavelength band is higher than in the other bands. And so the color that we perceive is a blue color. If something is perceived to be green, that means that the intensity of the emission, or the intensity of the reflection, is in the range of 0.49 to 0.54 microns. So whenever you're seeing colors, that just means that the colors, particularly colors of things that are not emitting, but they're just reflecting light, that just means that the other colors are being substantially absorbed so that what you see is just a red. This is the reason why if you take a red, if you go into a room that has a UV light, or let's say what we call those indigo lights, blue lights, or purple light, black lights. The black lights are primarily emitting in that blue and violet color. If the source of the light is just blue, what you're going to perceive is mostly things that have a very strong tint of blue. Even if the shirt is red in a invisible light, because it reflects mostly red light, if there's no red light in the blue light or the black light, then you're not going to see the red. So the visible light is being used as a reference here because it is a part of the thermal radiation range, but this applies to the entire thermal radiation range. If I have not only if this is all visible light, and I consider that the thermal radiation range also includes infrared, and it also includes the upper UV, a surface can absorb the upper UV, it can absorb the infrared, and it can also reflect UV, and it can also reflect infrared just like it does visible light. So depending on the type of surface, when I have irradiation from a source that could be all of the thermal radiation range, it could include the upper UV, it can include visible, and it can include infrared, which is all of the thermal radiation. These same things can happen if any combination of these ranges of the thermal radiation range is incident on a surface. That surface can reflect, it can absorb, and we'll talk a little bit later about it transmitting. Something that transmitting is something like a window pane. Often we want window panes if we want to be able to see into or out of a building. We want that window pane to be transparent to visible light, so that visible light can pass through it. I can see things that are outdoors from my office because the visible light that's reflecting off the plants, the buildings, the sidewalk is being reflected through the glass and into my eye so that I can perceive it. If I put window tint on that glass, it reduces the amount of visible light that can pass through, so I don't see the colors or the image with the same kind of intensity, because some of that energy is being absorbed by the tint and or being reflected by the tint. We have selective tints for windows because maybe we want to be able to see clearly, but we don't want very much infrared to be transmitted through the window pane so it doesn't get hot in the building. I want it to reflect the infrared. Well, I can put coatings on the outside of that glass that allow for visible light to pass through that coating, but infrared is reflected. So just like this surface is depicted to selectively reflect the red, but absorb the yellow, green, and blue as a part of this incident light. But if this incident light included upper UV and infrared, I could selectively do things to this surface. So maybe it absorbs all the infrared, or it reflects the infrared, or it absorbs part of the infrared and reflects other parts of the infrared. This concept is put into application in all kinds of window tints, designs of sunglasses, particular types of window panes, even surfaces that are used to collect water at night, such that their emissivity is very high and that they emit a lot of radiation to the sky at night, so that the temperature decreases and you can get dew to form on that surface, so you can collect water from the air without having to actually use air conditioning processes to get moisture out of the air. But this reflection and absorption here shown for the visible light range also applies to the invisible parts of the thermal radiation range, which include upper UV and infrared. It can be reflected. Those ranges can also be reflected and absorbed. Now here I have another expression of just a single temperature for the black body emissive power. So this is this EB lambda is the spectral black body emissive power. EB is the black body emissive power, which is just the area under the curve. And EB lambda is that spectral black body emissive power, which is a function of wavelength here. So that this is just one curve drawn qualitatively on this graph. Now here, I point this out because often we might be interested in, okay, well, if EB, which is the black body emissive power, is all the area under that curve, which is and gives me an expression of a heat flux, which is watts per meter squared. Well, what if I want to know, well, let's say in this problem, we look back here at the, let's say for the sun, the total area under that curve is over 64 million watts per square meter. But I'm interested in, well, how much of that is just in the visible light spectrum? You know, I know that from the upper part of the ultraviolet, including all the visible, including all the infrared, that it's over 64 million watts per meter squared. But I want to know, well, how much of that is just in the visible light spectrum? If this is from 0.4 to 0.76 microns. I want to know, well, if this is visible light, how much of that 64 million watts per meter squared falls in the visible light range? How much of it falls in the infrared? How much of it falls in the upper part of the UV? Well, we can use what we call black body radiation functions to determine exactly that. So here is a depiction of that same integral that I considered before, in that EB is just the integral from 0 to infinity of EB lambda d lambda. If I want to get the black body emissive power from 0 to a particular wavelength, I would just integrate from 0 to that particular wavelength, the expression of the spectral black body emissive power. And that will give me from 0 to here. If I wanted to consider, well, from 0 to E lambda 2, so the black body emissive power from 0 to lambda 2 would just be the integral from 0 to lambda 2 of EB lambda d lambda, not writing the functional dependence on the wavelength and temperature. It's just implied here. So this would give me all of the area from 0 to lambda 2 here. If I integrate from 0 to infinity, it gives me, you know, EB lambda. It gives me all the area under the entire curve here. So if I want to consider, well, how would I get it for just the visible light spectrum? If I wanted just the visible light spectrum, if EB is the integral from 0 to infinity of EB lambda d lambda, if I want to get just the portion that is in the visible light spectrum, EB from 0.4 to 0.6 microns would be equal to the integral from 0.4 to 0.76 microns of EB lambda d lambda. That's all. I would just integrate through those particular bounds. Now, this would require that I substitute in an expression for, well, what is EB lambda? That's an expression of the curve that describes this green line here. Well, one of the I wouldn't really call it a shortcut, and a method for rewriting this expression is the same as writing the integral from 0 to infinity, which will give me all the area under the curve, EB lambda d lambda, minus, well, actually, I'll write this a little differently. The integral from 0 to 0.76 EB lambda d lambda. So that would be all this area minus the integral from 0 to 0.46 EB lambda d lambda. I could write that the same way, right? If this first expression is just giving me what's between these two, well, if I take the integral from 0 to 0.76 and subtract from it the integral from 0 to 0.4, I'm just left with what's here. This concept allows us to use what we call black body radiation functions, and all they are expressions of integrals that are taken from lambda equals 0 to a particular wavelength for a given temperature. And we can define these fractions such that this expression of a fraction, if I divide EB, the black body emissive power divided by the black body emissive power, that's equal to a 1. And that will be equal to the integral from 0 to lambda, EB lambda d lambda, over the integral from 0 to lambda, 0 to infinity, EB lambda d lambda. So that's that expression. A fraction f, let's say from 0 to a lambda 1, would be written as the integral from 0 to lambda 1, EB lambda d lambda, over the integral from 0 to infinity of EB lambda d lambda, like this. So this fraction will be defined this way, so that this value of the fraction will be between 0 and 1, such that if lambda 1 is infinity, this fraction will just be a 1. If it's any other value, it will be some fraction that is a value that is less than 1. And so we can use those to define from 0 to 0.76 and 0 to 0.4, take the difference between the two, and that gives me this emission that occurs in this band that is the visible light spectrum. Well, I'm a minute over today, so next class again is your exam, your last exam, which is only going to cover chapters 8, 10, and 11. There won't be any coverage for chapter number 12. And I will be available in office hours tomorrow. So I hope you have a good rest of the day, and I will see you again on Wednesday. Have a good one.